Hi, this is Edward Awad. In this video, I'll be explaining how to calculate the amount of DNA amplified by PCR. I can give right away the formula to use, but that wouldn't help you understand the mathematical reasoning behind it. So let's start with one DNA molecule that contains a segment that we would like to amplify using PCR. Since DNA is a double helix, this molecule has two original DNA strands. In the first cycle of PCR, the strands separate. In the annealing step of the PCR cycle, the primers that recognize the targeted segment anneal in an anti-parallel position. The two primers are called forward and reverse primers. The forward primer anneal to a region towards the 5' end of a gene, while the reverse primer anneal to a region towards the 3' end of the gene. In the third step of the PCR cycle, the primers are extended as the DNA strands are used as templates to build new DNA. At the end of cycle 1, then, for every original DNA strand, we have a new DNA of indeterminate length that is produced. We call it indeterminate because an indeterminate part of the original DNA strand was copied along with the targeted segment as determined by the position of the primer. In cycle 2, primers anneal again to the original DNA strands as well as to the indeterminate strands, since the targeted segment was copied in cycle 1 into the indeterminate strands. At the end of cycle 2, a new indeterminate strand is produced from the original DNA strand, and a defined length DNA strand is produced from the indeterminate strand that was produced in cycle 1. What I mean by defined length DNA is the actual segment of DNA that we are targeting from amplification. So by the end of cycle 2 of PCR, for every original DNA strand, we end up with two indeterminate strands and one defined length strand. If you continue this exercise for cycle 3, you see that for every original DNA strand, we have now 3 indeterminate DNA strands and 4 defined length DNA strands. We notice here that the number of original DNA strands remains unchanged since they are used as templates, while the number of indeterminate DNA strands increases by 1 for every original DNA strand per cycle. For example, after 10 cycles of PCR, for every original DNA strand, we end up with 10 indeterminate strands. Now, since in general DNA is doubled with every cycle, the total number of copies of double-stranded DNA after a certain number of PCR cycles, let's call it n, is 2 to the power n. Since DNA is a double helix, the total number of copies of single-stranded DNA fragments is 2 times 2n, or 2 to the power n plus 1. If we do the math and add up the numbers after an n number of cycles, starting with one original DNA strand, we end up with n indeterminate DNA strands and 2 to the power n minus n plus 1 defined length DNA strands. Knowing that the total number of copies is 2 to the power n, the number of defined length copies becomes 2 to the power n minus the number of original DNA, which is 1, minus the number of indeterminate DNA, which is n. If we put the calculations in a table, this is what we get. Notice here that everything is doubled since DNA is a double helix, and what is shown here is the numbers for each type of single-stranded DNA. We looked so far at the number of single-stranded DNA, but what about the double-stranded DNA? What would be the number of copies of double-stranded DNA consisting of only defined length DNA? Some of the desired PCR products are most likely going to hybridize with the original template and fragments of indeterminate length. The number is 2 to the power n minus n plus 1 minus another n plus 1, which is equal to 2 to the power n minus 2 times n plus 1, where the second n plus 1 represents the original and indeterminate DNA fragments that can form a duplexes with defined length DNA. Therefore, the expected amplification of the desired defined length product, that is double-stranded, with respect to the original template concentration, let's call it X here, can thus be represented by this formula. This is often abbreviated to a simple rule of thumb for the amplification, and this equation becomes 2 to the power n minus 2n, the whole thing multiplied by the original amount of DNA. Let's take an example here. Let's assume that the original amount of DNA is 0.1 micrograms of DNA, and that we amplify it using 30 cycles of PCR. The amount of amplified DNA of defined length, double-stranded, would become this by applying the formula 2 to the power 30 minus 2 times 30, which is the number of cycles. The whole thing is multiplied by the original amount of DNA, which is 0.1 micrograms, to give us 107.37 million microgram of DNA.